Right. I must say that we are using our software because it's free. It's free. It's good. Python is also good. But one of the great softwares also for regression and econometrics is Stata. So when you have a free Stata, it's not free, but when you have a free Stata, then you use it. It is a bit more command, it's not much command driven as R. R is more programmable. There's a lot of programming in R, but there's a lot of clicking as well as, commands in Stata. So when you get it, use it. Today, we want to look at the assumptions of regression assumptions, and then which ones have been broken down. See, one of the thing about regression is that you should satisfy certain assumptions. Classical linear regression, they call it a Gauss-Markov property. So the relationship, there must be a linear relationship. The residuals must be normally distributed, independently and identically normally distributed with a zero mean and a constant variance, which is homoscedasticity. The independent variable must be exogenous. There must not be any high multi-collinearity. The residuals must be independent, uncorrelated with each other. The residuals must be uncorrelated with the dependent variable and even with the independent variables. And then the lag of the dependent variable must not influence the dependent variable of the present endogeneity. All of these assumptions, there must be outliers that have to be handled. Influential variables must be handled. Okay, so all of these, you want to check. You see, when you finish your regression, you got to use these diagnostics to check whether you have met these assumptions. All these assumptions have been met nicely. And those that have been violated are corrected. That is the essence of our presence today. So let's begin and look at these regression, situations. So once again, what we'll be doing is I'll be using the R software, and then we'll be analyzing these things using the R software. Okay. So let's start with the first one, multi-collinearity. I'll define all of these. And you can ask questions, because the more you ask questions, the more you can appreciate it. I'm giving you not just the theory, but also the practice of each one of them. What is multi-collinearity? Multi-collinearity exists when two independent variables are so highly correlated that it becomes difficult to disentangle the partial effect of one from the other on the dependent variable. So if you take experience and education, experience and education might interact with each other to the extent that their impact on your salary will not be too clear. So when your salary increases, it might be because of your education, but it might also be because of your experience. We know that separately. But it could be that it is your experience that led to your education. For example, there are some schools, courses, they will tell you that you must have maybe 5 years of experience, 2 years of experience. Else you cannot do or have that education. So your education itself is influenced by your experience before the education will influence your salary. Multi-collinearity is there. Your height and your weight might be influencing each other before they can affect, say, your blood pressure or your body mass index. And then dummies. Okay? A dummy can have a perfect multi-collinearity, because if you're not a male, you're a female, which is just 100% minus if you're a male. All of these are examples of multi-collinearity. And when it is so high, you are not able to know exactly which independent variable is truly affecting the dependent variable. And this is what would give you the clue that multicollinearity is happening or is there. That correlation, sometimes we call it a curse. The curse. The reason why it's a curse is because it will affect the R square. The R square can still be high when it is still bad, when the independent variables, when the coefficients are unbiased. So that principle of blue, best linear unbiased estimator for the beta, for the coefficient, it will no longer be unbiased. In other words, the expected value of the beta will no longer be the true beta. So you will have a problem with the beta, but you know that the coefficient, when you divide them by the standard errors, they give you the t value. So another problem is that the standard errors will be inflated when you have multicollinearity. The standard errors will be high. And you know when the standard error is high, because it's a denominator of the t statistic or the t value, the entire t value will go down. And when your entire t value is going down, it's not good, because when you compare that with a critical value, which is higher, you want your t statistic to always be bigger than the critical value for you to reject the null hypothesis. When the t statistic, which you see here, this formula here, when this t statistic is small, then the p-value will be big. And p-value is an error, the actual error you make in your research analysis. So if the error is big, you don't have enough gravitas. You don't have enough confidence level to be able to reject the null hypothesis. So you have a ripple effect of other negative things. In fact, you can even commit a type 1 error. Multicollinearity can be a case. So what do you do? Well, now that you know how bad it can be, okay, in other words, you don't even trust your result. The p-values are insignificant because of that. So what do you do? Well, let's look at our own that we had. Okay, this was our correlation matrix that we did, if you could remember very well. This very one, we did it in Excel using the coded Brukutu ventures. In case you have forgotten, it's there somewhere. And we're able to generate this correlation matrix. If you use R to do it, you will see that the top part will also be shown. Okay? But Excel is nice. It gives you only the down part here. And so it's quite cool when you're generating correlation matrix with Excel. But of course, if the data has got dummies, Excel will not be able to handle that. But later on, you're going to realize that you don't even need to bother about the correlation coefficient of dummies. Take note, write it down. In fact, I've asked you a question on this. The correlation coefficient of dummy variables, you don't need to bother about them, because obviously they are going to be highly correlated anyway. And you see that, pretty soon. So, how do you, first of all, detect multicollinearity? Well, one of the first things you would do is that multicollinearity has to do with independent variables, okay? So the first column here, which is for the dependent variable, is not packed. You cannot include that because this column here, Q, is for dependent variable. So the multicollinearity will start with the independent variables, which is this part here. Okay. This part here, starting from price. And then, of course, this part there. That is where you have that. So how do you do it? Well, first thing you got to do is check which of these independent variables have got a high correlation coefficient with the other independent variable. So I'm going to ask you some questions based on this, and then you tell me. Okay. Do I have the questions? Okay, I think the questions will come later. They'll come later. They'll come later. But when you look at it, you will notice that this is high, okay, between price and complement price. Between price and OTR is also high, okay. And which other one is high? Of course, not this. not the, because there's one here, which is between Rm and M. Okay. So these are signals that will give you the clue. Now, how do you really detect multicollinearity? This one is just a, just a preliminary way. So this indicates that there may be collinearity in those variables, but to check it properly, you have to use scatter plot. Scatter plots can be one way to detect possible multicollinearity. Another is to use a variance inflation factor. Variance inflation factor, ladies and gentlemen, is key because what it does is that it measures how high the variances are gone in the regression because of the collinearity among the regressors, among the predictors. How high? So you take each independent variable, you calculate a VIF, the variance inflation factor for that independent variable. But how do you calculate that? It's just 1 over 1 minus the R square. That is the R square for that particular independent variable. So what it means is that if you were to go by this, what it means is that you have to deal with simple regression for each independent variable. Okay, so you take price alone, you look at price alone, you handle that. You take complement price alone, you run the regression, look at the R square, you come and drop it in the formula. You take the income, you calculate it, you look at the R square, you come and drop it and calculate the VI one by one. Of course, the softwares can do that easily for you. Now, sometimes other people will use the tolerance level instead of the VIF. The tolerance level is a reciprocal of the VIF. Okay, that is how much you are willing to tolerate, multicollinearity. So that is how you do it. So what is the rule of thumb if you detect a number, particular number for multiple? How do you know that there is multiple or there is no multiple? How do you do that? Okay, you're going to do that. So one of the rules is that when the VIF is equal to 1, then there is no multicollinearity, just to say the least. In other words, that particular independent variable, xj, has no correlation with the other independent variables, which is cool. If you're going to get 1, that is good. That also means that the variance of the beta cap for that one is not inflated at all. But when the VIF is bigger than 5, then there is a modicum of multicollinearity in the data, in that particular variable. So let's say that price of Jane has got a VIF greater than, let's say, 6. Then it means that that price is correlated or multicollinear with another independent variable. But if it is bigger than 10, if the VIF is bigger than 10, that's dangerous. Dangerous multicollinearity of that variable. And that is what you want to deal with. Let me ask you a question. Yes, Emmanuel.
Prof, from this explanation, does it mean that if you compute one, is it one-way test or a double-way test? For example, your first example where VIF is equals to 1, where we have the variable j and another variable. If you do it for this, do you have to do the reverse for the same two variables again?
No. When you run the VIF, it will give you the VIF for each one of them.
Okay.
And the ones that have a VIF bigger are the ones you are going to clear them.
Pay attention to clear them. Okay.
Yes, you're going to drop them. By even dropping them, there is a rule before you drop them.
Okay. Thank you.
I'll talk about that very soon. But before we proceed, let me ask you, what do you think? Yes, Noah.
Yeah, Doc, what will be the practical interpretation of, say, moderate multicollinearity versus severe multicollinearity?
It means that that particular individual variable is is trying to act like I am also influencing the dependent variable, but actually I am tapping the energy from other variables to influence the dependent variable. So that variable itself is not really doing much in the model, but is taking energy from others. And that is why it is dangerously or severely multicollinear. But the moderate one means that it is tapping small energy from others. But then the higher one means it's tapping a lot of energy from multiple other independent variables. Practically, I'm speaking practically.
Okay.
Does that make sense?
Yeah, makes sense. Makes sense. Yeah. Thank you.
So you got to play your own role in the model. Don't go and take energy from other people. Yes, Obed.
Yeah, Prof. So what do you do if two variables are multicollinear, but in the model that you want to develop, you still want to maintain the two variables? For example, let's say the influence of education and then experience. Yes.
That's where we are going to. Don't worry at all.
Okay.
It's like asking the question, how do you deal with it if this is there? So look at how to deal with it. So let me ask you, what do you think the VIF value is in a simple regression? Who can tell me?
Yeah, Prof. I suggest it should be 1.
Exactly. You are thinking. Why?
Because it is only a single variable that is explaining the dependent variable, and therefore it will not depend on other variables to influence themselves.
Thank you. You are really thinking. Anyway, let's move on. So we are going to check first in our model whether it is there. Okay. So we're going to go into our analysis. This is normally done after you have run your regression, don't forget. So this is when you have generated your regression results. Oh. My PC is frozen.
It is giving us the time to go step by step, and we are enjoying it.
Yeah, so this is our data. Just to remind you, this was our data down here. You have all the commands, so I'm just trying to pick, and I know you all have the commands. And our gene multi was this. This was a regression that we did here, if you could remember. This is a regression. Now, once you are done with this, we can now go ahead and then look at the multicollinear situation. Now, if you check carefully, and I'm going to show you something in there. To be able to do this multicollinearity, if you have not already done so, you have to install and load the package called car. Okay. If you haven't done that, sometimes it's already there. If it's not already there, load it. And you all know how to load a package, car, and then you run it. Then, so I have loaded it. I'm going to run it here. So this is a package. And down here, you can see that it's done. Okay. Why is my computer not? It looks like it's getting frozen most of the time. All right. So now the next thing is to run the check multicollinearity. And to check multicollinearity, you run car : VIF, then your regression equation. Let's run that here. And look down there in the console. So it gives you this result for the independent variables. It gives you gene VIF result and gene VIF squared, raised to the power 1 divided by 2 times the degrees of freedom. We'll talk about all this. It gives you all of that. And you can check this second one. You can check the results for each one of them. Now, straight away as it is, I can explain, but you might not be able to fully get it. So the first thing you want to do is to round up your results. So you can create a rounding. And then you want to first check which ones have got a VIF greater than 10, because we said that is the dangerous one. That's a severe one. So this command will command R to try and detect which ones have got VIF greater than 10. So let's run that. And you can see down here, okay, again, it's the same thing. Okay, it's going to give you those that are greater than 10. Then you can now decide whether or not to drop them. You can also use this statement to check which independent variables are problematic. It will tell you, okay, by using something called the square root VIF of the GMT. Those great, I think this one rather gave the VIF. It did not give you those greater than 10. Now we want those greater than 10. Let's see that with this command. It tells you false, 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 because each one of them is not greater than 10. And you can see that from the right side here, okay, from the right side. The question is, what is the difference between the one on the left and the one on the right? We'll come back to that. So these commands that I've just run, you have them all here. And then you can run them. These are the results. The question, however, is we have two of the methods. We have the GIF degrees of freedom, GVIF, and a GVIF raised to the power blah, blah, blah. Which did you use? Now, the generalized VIF was by a man known as Fox and Monette in 1992. That one uses dummy independent variables, or in case they are quadratics or polynomials. If the data is continuous variables, then the generalized VIF and the normal VIF are the same. So that is the first one. If they are categorical variables, okay, we are going to get one of the GIF value for each of the dummy. Example, you're going to have one value for all age groups, if they are age group, another value for all religions, okay, if they are religions, several religions. You're going to just have one value for them. In other words, the other religious denominations inside religion, you don't see them. I'll give you an example of what I mean. So if when you look here, you see location, you have it for, oh, it's not highlighted. Yeah, you have it for that. But the location is both urban and rural. So you don't really know which one you are getting here. When you take occupation, it gives you one value, but you don't know which type of occupation it is actually giving you. And religion, the same thing. You don't know which type of religion it is actually giving you. So the variables which require more than one coefficient and therefore more than 1 degrees of freedom are the ones that are typically evaluated or assessed if you use the GVI. Then Fox and Monette suggested that you can use this second formula, the GVIF raised to the power 1 divided by the 2 times the degrees of freedom. Why? Because it makes the other one, the first one, comparable across dimensions or different coefficients. So the second one is the one you will use, and is the one that reduces the previous one to a linear measure. And it's similar to if you take the square root of the normal VIF. So if you take the square root of the VIF itself, you will get a second one. And that is the one that we use. That's the one that I like to use. That's the one you like to use. However, there's a snag here, and I wanted you to note that. What do you do with when you get an independent variable with the largest VIF? The first thing you're going to do is that, and I'm coming back to answer your question. So suppose we were to use this second one here, this first one. You can see that majority of them, majority of them are above 10. But of course, I told you that the one we use is this. Okay. But suppose we're using that, majority of them are above 10. And because they are above 10, you're going to look for the one with the highest VIF. And that one is occupation here. Now remember, there's a problem with dealing with multicollinearity of dummy variables. I'll talk about that, but I've spoken about that privately before. You don't look at it. You don't look at multicollinearity for dummy variables. And you can see why clearly, because the levels are not even seen. It doesn't tell you which kind of level that we are actually calculating their dummies, their VIFs. So, but if they were all continuous variables, the one with the highest is the one you're going to remove first. But you don't just remove that. It has a higher VIF, okay, and then you check the p-value of it in the way. You got to go check the p-value, okay, and when you go up here and you try and check the VIF again, you wouldn't even know which one p-value you are checking because there are quite a number of them. But let's assume that we are checking occupation, and then you can see that they are all significant, but then they are highly correlated. Of course, they should be highly correlated. They are dummies, okay? But suppose this one is the biggest one in a continuous fashion. What you would do is to remove that one and then rebuild the entire model again. So coming back to your question you asked, I think it's Noah. You will remove the one with the largest VIF, rebuild the model, and check whether the other variables that were insignificant are now significant. This is important. If they were insignificant and they are now significant, then it means that that guy you removed was the one causing their insignificance. However, if they were insignificant and they are still insignificant, then that guy is not causing any harm anyway. If the R square is not reduced, that guy has not punished anybody when you removed it. But the moment you remove this, the R square has gone up. Then it means that guy was the one causing the R square to be down. So it must stay there. What if the one you are removing, and this is key, is the one that your literature is all about? What if that is a variable you are writing a lot of literature review on? Then you got to think. Then you got to keep the multicollinearity and use lasso regression. We said it before, or ridge regression. You remember that? And you still keep that. I'll talk about that briefly, but I just wanted to know that. So that's what you do. You rebuild the model, you check the p-value. It's not good practice. And this is the point I said. It's not a good practice to consider even the VIF for dummies. Why? Because you're already correlated with other categories, and therefore they will obviously have high VIF. So it's like a dummy, like male and female. You know, opposite of one is the other directly. So you ignore the dummies. That's the key point. So you only focus on these ones, okay, and ignore the dummies, and focus on the continuous variables. Now, those independent variables with insignificant p-values, I've said this already, may also be removed and another model be rebuilt. That is, if their removal causes an impact in the entire model. But if their removal does not cause an impact, you bring them back and go and deal with that multicollinearity proper than just removing things. So that dropping will continue until a minimal or no multicollinearity is detected in the model. And then, of course, you have to check the R squared to see whether it's affected. See, in our case, there is no issue there, so that is why. But you're going to see that for some other approaches, there will be an issue. Let's look at the multicollinearity better now, using another package, which is called J2. It will show you something interesting. So the previous one was CAR. Now we are using J2s. So when you run the J2s, and then you run the regression model, you get this kind of results. You see, J2s gives you a very nice result. Okay. So you have the p-value, you have the model, it tells you that it's OLS regression. These are the standard errors. The p-values are on the far right. Okay, it's cool. It's fine. Now, we want to check for multicollinearity. Again, using the Fox and Monette, GVIs. Okay. And we are going to focus on the continuous variables. If you show this one here, on the far right, it will give you the VIF of the result. And you can see on the far right, the VIF for each independent variable. Now, already we have said that you have to what? Ignore the dummies. So these ones will be gone. The dummies will be gone. And so we're going to deal with just the price, the complement price, as well as the income. So when you look at that, what do you say? How do you see it? Well, the first one is price. You can see that price has got a higher VIF. These other two are not a problem. Now, the question we have to check is, if you look at price with a higher VIF, look at this p-value. I mean, look at the p-value for some of them. This one here, which is income. Income has got a p-value which is 20%. So now you got to remove price, run the data, and check the p-value for M. If the p-value for M is still not affected, that is, it doesn't come down, you bring back price. That's how it works. You bring back price into the model. I'm not going to do that. You can do that. So that is how you handle this very one. We've already known the result. This is just another way to detect multicollinearity. So how do you deal with it? We've said that multicollinearity will affect the coefficient, and of course, it will go a long way to affect the p-values, even though it doesn't affect the goodness of it, the F statistic. So how do you deal with it? You remove one of them and rerun the model. Another way of dealing with multico is that you can combine the predictors in some way, especially when they are dummies. You can combine the independent variables. So you multiply one by the other, or subtract one from the other, or add one to the other. Okay. There are ways you can combine them. And that combining is a form of principal component analysis. Okay. So you can perform a PCA. PCA will help you to do that combination. If you don't know PCA, in one of my videos, I've explained PCA there, so you can check it. Or you can also do partial least squares regression to be able to handle the multiple. But, like I said, you can keep everything in there. The range regression, the lasso regression, and then the elastic net regression. These regression deal with multicollinearity directly without even having to remove any variable. They are cool, but you got to learn how to do them. That's it. So this is how you handle multicollinearity in this very instance. I am not going to look much into multicollinearity because in our own, there was not much issues with multicollinearity. No. We are ready to look at the next regression diagnostic, and that is the assumption of normality. One of the assumptions of regression was that the expected value of the errors should be 0. You guys remember, it was a very cool one. That means the mean of the residuals should be 0. And when that is so, then we say the errors or the residuals are normally distributed with a 0 mean. How do you check that? It's a very simple thing. Just type mean of the residuals of your model. That's it. And check the value. If the value is approximately 0, you have passed the test. Okay, so let's go to our model to check. Okay, this is it. Okay, so run this and then see the result. And I'm going to run that. Look down here. The results are down here, which is negative 2.777. Okay, with the exponent of minus 17, which means that there are 17 zeros before the 7. Or there are negative 17 zeros before the 7. So it just goes to show that this is purely 0. That's all it means, 0. So the expected value of the errors are truly 0. Assumption of normality is passed. So you say it. You just say it in your work that we checked and then we realized that the residuals are normally distributed with a zero mean. So we've satisfied that assumption. Done deal. Next one is the test of normality. You see, you can have the assumption of normality, and you can also have the test of the normality. There are certain things in life that are Poisson distributed, like the number of people queuing in front of a desk per hour. There are other things that are Weibull distributed. Some are Leontief distributed. Certain things are normally distributed. Certain things are half normally distributed. Certain things are gamma distributed, truncated distributed, and several distributions. So you want to check the normality also using plots and also using test statistic. In fact, the test statistic is the one we used. I didn't write the test statistics for you to see. So you can use PP plots, quantile normal probability plot. You can use kernel density plot or histogram of the residuals. And then you can also use the Shapiro-Wilk test. You can do that. And this is a test statistic, which you got to learn. I mean, sometimes it's good to know where all of these things are coming. So how do you do these plots? Well, it's very simple. The plots will just confirm some of our things. But please note that it's not all the plots that will confirm residual, expected value of the residual being equal to 0. If there's a problem, some of them may suggest something else than that. So let's look at the first plot, QQ plot. Okay. The studentized residual plot. This is the command I'm going to use. So this is the plot. I'm just trying to show the plot. I'm using a beautiful one, actually. So this is a plot. You can see that the plots here are supposed to be seated on the blue line and not too deviational from the space. Of course, the other things that are being used here, which we'll talk about later, like outliers. So you can see the observation 14, observation 4. These guys could be outliers in there. So that is a plot there. I wish I can show another plot. I don't want to draw this thing.
The plot, what's the meaning? I can see the line in the middle, and there are some scatter points.
So the line is how the actual residual is supposed to be.
The one in the middle?
Yeah, the blue line.
Good. Okay.
Then the dots are your... Okay, the line is the predicted. The dots
the best
are
line
the actual one that you got from your gene multi data.
Okay.
So ideally, the dots are supposed to be seated
on the middle one.
On the blue one, exactly.
Okay,
the middle one.
To show that the deviation is not far.
Exactly.
Okay.
But that shaded area is also telling you how far all of them are within a certain limitation. So even though they are not directly on the blue line, do they fall within the atmosphere of the blue line?
Okay.
And then it will give you an idea as to whether it is normally distributed or is not normally distributed. And while this is great, sometimes I guarantee you, sometimes you'll be confused.
Yes, sir.
Just using the line alone can be confusing.
Okay. Also, what is the major take home for this line? What can we conclude on this line? Is there any key learning point from this line?
That is why I said that sometimes you can be confused. So when you look at the lines, it appears to me that they are not normally distributed.
Okay.
It appears to me. But again, you would always want to check it with what?
Second confirmation.
Exactly. With a test. Okay. And the test is the Shapiro test.
Okay, Shapiro, yeah. Okay.
So this is the Shapiro test. We are going to check the Shapiro test here.
Okay.
This one here. And it will confirm whether or not they are normally distributed or not.
Okay.
Let's see. So you run this Shapiro test.
Okay.
Oh, it's frozen again. Okay, let's go.
Okay, mine
And
is
down
it says
here,
W is equals to 0.99974. P value is equal to 0.0002009.
exactly. That W is a test statistic.
Okay.
Okay. And then the p-value is, now we've said this before, that if you want to prove that is normal, the p-value must be bigger than 5%. We said it before. And if the p-value is not bigger than 5%, then it's not normally distributed. So the Shapiro test clearly tells you that the graph you are seeing here is an indication that they are not normally distributed. So the expected value of the residuals can be equal to 0, but it's not normally distributed. That's what it means. Okay. So what could cause something like that? You will see how to correct this. Okay. So the conclusion we made here is that the Shapiro test tends to be high, close to 1, for samples that are normal. So when the value is close to 1, okay, that is for samples that are normally distributed. You can see that the p-value is not like that. In fact, let's look at another residual test. There are several residual tests to just confirm. There's another one that I have here, okay, for library OLS RR. You have it in yours. Okay, it appears that I've not installed it. Okay. And when you check it, okay, so it's quite strange, eh? When you check it, you see that the p-value is bigger than 5%, which shows that the data is normally distributed. Let me confirm that. Okay? I need to install this package quickly. It's called OLSRR. OLSRR. There you go. And then you run that library. It looks like it's normally distributed. It looks like the Shapiro test will give you a different, let me run the test and then you see. Oh. And now let's see. Okay, good. So let's see. So it gives you these tests, which are really, well, it confirms what we have, right? It gives you the Kolmogorov-Smirnov test, the other tests, and the Sindalin and other tests. Some of them have got a p-value which is more than 5%, some of them. So sometimes you get confused as to exactly which one to use. Okay. So I always say that always stick to the Shapiro work test. And from that, you will see that the data is not normally distributed in this context. That is it. But here's a key point on normality, because sometimes when you use some of these things, they will get a bit confusing. It is only needed for valid hypothesis testing. Normality. It's not a big deal. That's the point. Okay. The assumption makes it possible for the p-values or the F statistics to be valid. Okay. Actually, when you look at OLS regression, it only requires that the residuals are independently and identically distributed, okay, and not necessarily that they must by force be, normally distributed. And when you have outliers in the data and you have small sample in the data, obviously non-normality will happen. Like in our case, our sample is 40, okay, and we spotted possible outliers. Okay. And that non-normality will require a misspecified, will lead to a misspecified errors in the model. And we will have to correct that. In our next one, you will see that we are correcting that by using non-linearity in the model instead of linearity in the model. And you will see that it will correct those things. We'll come back to that. Under heteroscedasticity, I want you to note that normality is about the errors. Heteroscedasticity is about the errors. Autocorrelation is about the errors. So they are all connected. So as you try and solve one, you'll be solving all the others. So sometimes you don't need to go through all these steps I'm doing one by one, one by one. No, you have to do one and it solves all of them. Okay? So think about that and we'll come back to that. So normality is not a big issue. And in this very example, it appears that there is some sort of non-normality here. So we continue. What if the residuals are not normal in this case? This is how you handle non-normality. I've given you all the solution you can use to handle non-normality. You have to correct the residuals, the standard errors. And so you got to use something called heteroscedastic autocorrelated consistent standard errors. Or you got to use something called heteroscedasticity corrected covariance matrix. You will slot that into the model, and it is between the value of 0 and 7. You can try all of them. It will solve the normality issue. You can use bootstrapping. Okay, bootstrapping, we use less assumptions because it's more non-parametric. You can use trimming and winsorizing. It's a kind of robust regression. You can use data transformation. We'll deal with that. Okay, next time. All of these are ways to solve other things, but they will automatically solve the non-normality issue. That's what I'm trying to say. Data transformation means that you may have to take the log of the dependent variable, the log of the independent variables, the square of some of the independent variables, and the square root of some of the independent variables, or the exponent, or the arc sign, or the inverse hyperbolics. Okay. All of these are ways you can use to handle non-normality, which will also handle other things, which we shall talk about later. You can use other non-parametric methods, okay, and different kind of non-parametric methods to handle non-normality. You can use nonlinear models completely away from the linear models like OLS. You can rather use nonlinear models like WLS, which is weighted least squares, GLS, which is generalized least squares, FGLS, which is feasible generalized least squares, 2SLS, which is two-stage least squares, and GLM, which is generalized linear model. You shall look at them. You shall look at them. It's just to load you up to see that there's a solution if this is a big issue there. Let's look at the next assumption and correct it. This one is cool and it's easy one. And this is assumption of linearity of the independent variable. Now let me give you some theory to help you here. Look at this model. Is it a linear model? Yes. This is a linear model.
Yes, that's it.
Suppose we fit this linear model, but the data set we are using is nonlinear. So we have a data set, and then we rather fit a set of data generated from a nonlinear model like this one. This one is nonlinear. What makes it nonlinear? Because it's a fraction.
It's a fractional form.
Good. And so once you do that, and you go and pick, once you estimate this and you pick the residuals, you will have residuals which is equal to the actual minus the predicted. And the predicted is going to be these ones. Okay, sorry, the actual is going to be this one here. This is actual, as you can see up here. And the predicted, okay, remember, is the actual here minus the predicted. And the actual is this minus the predicted. The predicted is that. Okay, which will have an error subtracted from the original error. And this is nonlinear. All of this is nonlinear. So your residual plot will show a curve instead of a line. So you have a principle, you have an embedded non-linear hyperbolic or parabolic or quadratic or a curve, something. You're going to have that. Why? Because you have generated a nonlinear residuals. That is if you use, that kind of a model. So how do you handle that? Let's go and check our own to see whether it is exhibiting linearity of the independent variables or it's not exhibiting linearity of the independent variables. And one way you can do that is called CR plot. It's called component residual plot. It's a very, very good way to see if the independent variables are linearly connected with the dependent variable. If you go to this one and run that model, this is what you see on the right side here. Guys, like I said, all of these things, you can correct them easily. I'm just picking them one by one. So you don't need to go through all of this in your normal way, unless you want to play along with it. So this will give you, for each independent variable, it will tell you how the residual is correlated with that independent variable. And look at it carefully here. You see the dummies are also there, okay? And that is why it's not good to look at dummies, because the dummies one, you cannot detect even, the dummy itself is not linear, as you guys know. So what you notice from the ones that are not dummies is that you have the blue line and then you have the red line. The blue line is the true linear one. The red-like or the pink-like one is the one from your estimated residuals, the one from your data. And the blue is the one that is supposed to be the proper one. And so if it is linear, you will see that once again, the red line or the pink line will sit nicely on the blue line individually. It appears that for price, there's some kind of, yes.
Prof, a minute. We can see multiple infographics on the screen. The left hand side where your cursor is, and the right hand side. So we want to know
which one is
represent
which?
One. The first one on your upper.
The first one is for side. Price.
Oh, good, okay.
The second one is for component, complement price.
Okay.
And then the third one is for income.
Okay.
Then you have location, occupation, and then religion. So it gives you for each independent variable.
Good. Now we have an idea of what they represent. Okay.
So when you take price alone, you will see that the residuals, the component plus the residuals, you see that for price, it appears that price is seated on the blue line.
Yes, quite better.
So price appears to be linear.
Linear, that's good.
But when you look at complement price, you will see that the red line is kind of changing a bit from the linearity.
Yeah, deviating.
Yes. Very good. Yeah. When you look at income, it is also appearing to be slightly deviating.
Deviating is true. It's true.
As for these ones, you don't even have to look at them because they are dummies.
Dummies. That's good. Now they
so
make
it gives you a fair idea that there appears to be some modicum of non-linearity.
Good. Okay.
Generally speaking.
Okay.
There appears.
So as soon as they deviate, that's a conclusion.
Yeah, that is a possible conclusion. Possible. Possible.
I'm okay.
Now, the key point is that you got to check it whether that is really, really true.
Okay.
Now, what it does is that the line will ensure that the residuals don't form a strong pattern. So they should be randomly and uniformly scattered around the x-axis. And if you have models where the residuals of one independent variable against the dependent variable, and then you add a line of the best fit, which is exactly what we have there, then you can check the movement, which we have done. And we conclude here that a significant difference between the residual line and the component line will show non-linear length, which we have seen. Okay? The residual line was a blue line. The component line was a red line. When they are deviating, that's what we mean by significant difference. Then there's a possibility of non-linearity. Okay? And we can sense that with complement price and that of income. Price seems to be okay. So that is how it is here. You see, I use a different approach to check it, and you can see that it's a similar thing that is also here. You can still check it further. Okay, you can still check it further using another thing called residual plot GenMult. This one, when you use this one, is just several checks. That will also tell you that the residuals are plotted against the fitted you plot a fitted against the predicted variable. And if any of these plots shows some shapes, systematic shapes, then the linear model is not appropriate. So you got to use a nonlinear model. Okay. So you can do the residual plot to give you, to be honest, it will give you a similar thing like with the one we saw. Look at it here. Price again seems to be seated on the dotted line. You know, complement price seems to be now quadratic. You can see that.
Yes.
Again, reflecting what we said that it might be nonlinear. It might be nonlinear there. And any income too, you can see clearly that it appears to be nonlinear. It's not straight line, it's rather curvilinear. And then of course we don't need the dummies, like I told you. So this one didn't even bring the dummies like the other one did. So what do all this mean? Okay. If you sense some pattern in the residual and the fitted, okay, that means that the residuals are not randomly distributed. You have to fix the problem. Okay. And we can see that in our own, that there seems to be some curvilinear situations. So we're going to apply log transformation on the dependent variable. So our dependent variable is quantity demanded. We're going to apply log transformation on the dependent variable and then rebuild a new model. Guys, here you're going to see something interesting. How do you do that? This is how you do it. Let me just explain. So here I create a log of the quantity demanded. You see, at first it was just kill. So I now say that I want you to create me a new value called log of kill. That's what I have here. So I create a log of kill and I call it gen log kill. So I'm going to go to the thing and create. It's just that you can just do this in Excel, but it's good you do it in R as well. That's better. So this command here will create the log of kill. Command 357. I'm doing that here. It's done. It's created down here. Then you're going to run the entire model again based on this log of kill. You only log the kill. So you run this model again. And just watch what will happen compared to the previous one. Now, before we go there, I want you to remember the previous result. I just want to show the previous result here so that you guys can appreciate it more. Yeah, sometimes you just compare your results. You have to go and run the previous ones first. I can't find it. Let me see. Let me use the J2's one because this other one is not giving me. Okay, I think it's it. Okay, that's it. So if you look at this results, you will notice that some of them are significant, some of them are not significant. Okay, so now let's go back and look at when we logged the dependent variable. So I'm going to run this command this time with the dependent variable logs, and I call it gen log linear. And look at it here. Instead of using kill, I'm using log of kill now. And then I run this. Look at the results. Do you see a difference between this one and the previous one? But let me go and remind you of the previous one because the actual previous one wasn't here. Where is that? I know that some of you might be confused if I don't bring the previous one. So I'm just, okay, so this is the original one. Look at the original one here. The original one, look at the stars. Okay. Do you realize that these ones are not significant? Do you see that? Okay. That is without the logo. But now, watch the one with the log. This is the one with the log. I'm going to show you that one down here. The one with the log is this, and compare the two. See the first one, this second one. What do you say quickly from this?
The one with the log is more significant because most of income and location that were not having stars are not having at least one star.
Exactly. So you can see that it's created a more significant result from that just by taking the log. of the dependent variable. It solves a lot of issues. And if you go and run some of the problems the previous one is having, you will not have that problem with this one. I'm telling you, you will not. I don't have the time to do that, but you can just go and run all these other analysis on this and you know. However, one of the things you will notice is that the coefficient will change here. So if you check here, the coefficients have changed. Okay. I mean, you can check that with the previous one. Look at the previous one. The coefficient for the price was negative 3.15. This time the price is negative 2.1. Now, it doesn't matter. Also, I want you to know that since it's now log, the way you will interpret them will also slightly change. But again, that's not a problem. Okay? The key interesting thing about all this is that you've been able to, just taking the log transformation, you have significated, that's a new word I'm using. You've significated most of the independent variables. Okay? So that's that there. Now you can check the residual plot. Let's check the residual plot. Like I said, you can check the plot to see. Now, the previous guy, we didn't have a lot of independent variables. This was a residual plot. Yeah. You can see it on the right here. Now, with this new one, let's do the CR plot. Okay, I'm coming to do the CR plot with this new logged one. There you go. Now you can see. Maybe not much difference, but let's see. This was the previous one. Look at the previous one. Hold on. So that is the previous one. Look at price. Okay. And then the new one, this is price. Does it look like the new one has got slight seated than the previous? Look at the previous again. It doesn't look like there's much difference, is there?
But there's a little difference. It looks like the second one is much more fitted.
Yeah, it appears. This is the second one. That's the first one. That's the second one. Yeah, the second one seems to be a bit closer to the blue lines, huh?
Yes, yes.
Yeah, a bit closer to the blue lines. Cool. So the second one is showing no patterns in the residuals, no patterns there, with them seated on the blue line than the second one, than the first one. Another thing you can check is the other residual plot. Okay, there was another plot of residuals. This one. I've forgotten the previous one, but guys, when you check this one, again, there seems to be no difference, but when you go and check it, maybe this one will have slight better situation than the previous ones. Now look at what is this result? Okay, so look at it's giving some interesting statistics here, but I'm interested in the graph here. So look at the graph here. It seems to be slight because if I should compare that with this one is here. Where is that? I think the previous one is hidden. This was another graph to reflect the previous one. And look at the summary of the results. This is a summary of the result for the old one. You can see the results of the old one is this, and the summary of the new one is a result. You can see that the new one has got more significant variables than the old one. So in short, when you are able to correct for linearity, you are likely to get significant results. And this, by the way, will solve another problem, which we haven't come to. Okay, but we'll look at that problem later. Okay. So linearity, can cause some insignificant result. That's the whole point. It means that you have forced something that is not linear on a linear line. It's rather supposed to have been put on a nonlinear graph or a nonlinear model, but you forced it to be linear. Now, I've given you a link for you to check other regression diagnostics. because there are two main ones that I want you to note. We'll look at them next time. But I want to, before we look at those, they are very powerful. Heteroscedasticity and autocorrelation, we'll look at them deeply. But before that, I want you to know that there are other ones you can check. Some of them are assumptions, some of them are not assumptions, they are just checks. And this link will give you them. I'm going to pick one of them one by one. Yes, Obe.
Yeah, Prof, let me take you back small. When you log your variables, is it important to show it on your research paper?
Yes.
That the variables has been actually
Yes,
logged?
you have to. So you have to write log of kill. So
okay.
You will have a model which has kill, and you have a model which has log of kill. If you rather want to use the log of kill, then you don't even write the first one. You rather write log of kill in the paper. In the paper. So in your formulation of the model, you will use the log of kill instead of the kill. You remember how when we formulated the model? Yeah.
Yes, please. Thank you.
All right. Okay, so one of them is influential variables. Okay, observations that exert unnecessary influence on the estimate. You got to know the difference between outliers and influences. Okay, outliers have large residuals. Influences, their removal will change everything. Okay. I used to draw a graph to show which variable is an outlier and which is an influencer. Let me just show you something. Suppose you have a scatter plot like this. Okay, let me do it here. Suppose you have a scatter plot. This is an XY graph. And you have a variable here. And then you draw a regression line like that. And then you have another scatter plot like this. You have a variable here. And then you have a regression line like that. I have a data set of A and I have that of B. Which one is exhibiting influential variable and which one is exhibiting outlier? Which one is an influencer and which one is an outlier? And when I say it's an influencer, I'm talking about the stars. Okay? So let's say this one here. Let's say Y here and then W here. Which one is an influencer and which one is an outlier? Which one is more dangerous, by the way? An outlier or influencer? Influencers are more dangerous. An outlier is not as dangerous as an influencer.
Okay.
Why? Because an influencer must be an outlier for you to be an influencer. But you don't have to be an influencer to be an outlier. But you have to be an outlier to be an influencer. Influence can be seen as a product of leverage and outliers. And you can check them. Okay, there are two types of methods to check outliers. You can use the residuals, the leverage, the cookie distance, the defects. All of these are ways of checking for outliers and influences. Like I said, these are just extra things that you should learn on your own. Okay, but I've given you the information here. I will encourage you to learn on your own. So the question is that, are there outliers? If you run these models, and I'm not going to go into details of them. If you run these models, and again, you can check the video here, you will notice this is the result. It will give you the result using the residual versus the fitted, as well as the quantum normal probability plot and several other plots. What is the clue there? If you check the observation, you see that one of the observation 24 is here, 24 is there, 24 is there, 24 is there. So 24 is appearing to act like, a troublemaker. So you can use AV plot, and the AV plot will bring other variables, but 24 will also be there. You can use a limitation of that, and you can see that 24 will still be there. You can test for the outliers, and you use the Bonferroni test for outliers. And if the unadjusted value is less than 5%, then it means that there may be outliers. If we check our own, it is 0.07, which indicates that there is sort of no outliers. There's no outliers because the p-value is bigger than 5% instead of it being smaller than 5%. Okay. Because normally the null hypothesis is that the observation is an outlier. And when the p-value is bigger, you reject that null hypothesis and conclude in favor of the alternative. Note that when you are doing outlier test, it's the same as the normality test, where p-value is rather for the one you are dealing with. Okay. You can also check for influential variables using all of this information I've given you. Like I said, this is not my main concern, but it's for you to check on yourself. And you will notice that some observations are unusual, few of them, but they are not big issues to affect the entire regression. So if there are outliers, how do you handle them? Robust regression will handle that. Okay? Robust regression will handle that. Sometimes this is done by iterated weighted least squares. It will use the weight to correct for the situation. But then the software does it easily for you. If you command a package called mass, you can use the OLS when the data is contaminated with outliers or influencer. You can still use the OLS, okay? And then you use this robust regression to run the thing. The robust regression is RLM instead of the LM. So it is robust linear model instead of the linear model. We can run this robust regression. And when you run it and you check the results, you see that it solves most of the situations. You can check for all of these regression analysis. But I'm just slightly rushing here, but I just wanted to know that you can check everything. One command can give you everything to see whether your model has got problems or doesn't have problems. And that model is this. So you can say that GV model, and then let's take our gene multi and summarize the GV model. It will give you every result that you need. Yeah. It will tell you the skewness, the ketosis, the linearity, and the heteroscedasticity. It will tell you whether it's acceptable or it's not acceptable, whether you should go ahead or you should not go ahead. It will give you for each one of them. And the interpretation of each of these results is also here. For example, I will not talk about heteroscedasticity because we'll come back to it. For example, when you look at a link function, it is trying to find out whether the dependent variable is continuous or is categorical. If the p-value is less than 5%, you reject the null hypothesis, which shows that you should use an alternative form of the model. In other words, it is not continuous, and so you got to use an alternative form of the model, like logistic model or binomial model, which deals with limited dependent variable, which means that one of the dependent variable is a dummy, more or less. We'll look at that in the future, the dependent variable. And this is done using the generalized linear model. So each one of these things will tell you how the model looks like. But the key point is this. When you try and correct for heteroscedasticity and autocorrelation, all of this will be solved as well. Take note of that. That's the most important thing. And that is why I'm not focusing too much on this. So that is it for today. What we are going to do next time is that I'll take my time and handle heteroscedasticity in the model, handle autocorrelation in the model, and then we'll use that to solve all of these problems. because they are the underlying factors. Ladies and gentlemen, that brings us to the end of the entire Abudo. Now, at this stage, I know if you have a question, you can ask. Yeah, I know you may have a question. It's from your questions I will address it.